Welcome to Lecture 4 of Microeconomic Analysis 1 with me, Dr. Craig Webb. In today's lecture, we'll be starting our work on consumer theory, and we'll develop some of the basic tools and we'll continue to develop more tools in the next lecture to model consumer behaviour so that we can analyse demand and welfare questions later on. Now, the basic assumption for consumer theory is that when we think of a consumer in microeconomics, we imagine simply that they make choices in such a way that they choose the thing they prefer the most and that they can afford. So it starts with a simple idea, which is expressed in everyday language. The consumer chooses the thing that they can afford, that they most prefer. Okay? Now, part of our job constructing economic models is to translate that basic sentence from English into a language that we're going to develop. We're going to use all sorts of tools like indifference curves, marginal rates of substitutions, budget lines, utility functions, and so on. All of these are constructed so as we can model that very simple idea that consumers choose the thing they prefer the most and that they can afford it. Okay, so let's get started developing our model of a consumer. Okay, so let's present the basic ingredients of our model that we will use for studying consumer theory. So we're going to assume that there are two goods, okay, which will denote goods 1 and good 2. Now, in principle, these could be anything that the consumer likes and wants to have, but we're going to make two assumptions. First of all, we'll assume that both of these goods are perfectly divisible. Okay, now this means that we can essentially, our consumer will be able to consume the good in any unit. So they don't just have to have 1 unit or 2 units. They can have 1.5, 1 3/4. They can have the square root of 2 units of this good if they wish. So any amount is acceptable. Clearly, this is just an abstraction to make the maths more convenient. You know, if our equations are going to have solutions, then something like this is really going to help. The second assumption we will make is that our goods, each good is what we call homogeneous. Okay? Now, homogeneous means, it does not mean that goods 1 and 2 are the same. What it means is that if I look at good 1, then any unit of good 1 is the same as any other unit of good 1. Okay, so if good 1 represented amounts of apples, for instance, then we wouldn't be looking at green apples, red apples, pink ladies, golden delicious, and all these various types. We're just going to say there is one type and all units are the same. Okay, so again, this is a simplifying assumption. But it's going to allow us to do the following thing. It's going to allow us to think that essentially we'll be able to consume these two goods in any number and any unit of these two goods are the same. Okay. Now, the consumer, what are they going to choose? So the object of choice, or the objects of choice, are what we call bundles. Okay, so a bundle, sometimes it's called a basket of goods. So a bundle, which will denote something like this, A is a bundle, and it's a 2-dimensional object. So A1 and A2, it's described by 2 numbers. And the interpretation is quite simple. If I have bundle A, then this gives me A1 units. Now, this is just a number, so it gives me some number A1 units of good 1, and it gives me some number A2 units of good 2. Okay, similarly, if I have the bundle B. This might give me a different quantity of good 1, B1, and a different quantity of good 2, B2. Okay, now these are the objects that our consumer is going to be comparing in a sense that we'll make concrete in a minute. But first of all, let's kind of represent these objects diagrammatically. Okay, so we're going to, if I draw a diagram, so let's just draw a vertical. Something like this. And on the horizontal axis, I will put good 1. And on the vertical axis, we'll label this good 2. Okay, let's put 0 here. Whenever we start a diagram in microeconomics, or any of your economics courses, we need to see labels on the axis explaining what all this means. So how would we represent a bundle like A? So if I take, now this entire space here is called it's what we call the positive orthant of the plane. So let me just explain why. So in mathematics we use the boldface R like this to represent the real numbers. So this is all the numbers that are greater than minus infinity and less than infinity. So this is an interval. Now we use R plus to denote the positive real numbers, or the non-negative real numbers. Okay, so this is starting and including 0. Sometimes you see plus plus here if we're going to exclude 0, but this R plus is the non-negative numbers starting from 0 to infinity. Okay, so each of these numbers, A1, belongs to this interval, and A2 belongs to this interval. Okay, but these are two-dimensional. So what I could say is that a bundle each number is a positive real number, but I need 2 of them. Okay, so this is the positive orthant of the plane. So I'm essentially taking 1 copy of the real numbers in this direction and 1 copy of the real numbers in this direction. This notation here means belongs to, or is an element of. So a bundle belongs to this space somewhere. Okay, so if I just pick any point here, A, and label it, then I can read off along the axis that this bundle contains A1 units of good 1 and A2 units of good 2. Okay, and if I take a different bundle, B, I can read off again from the axis that B contains more of good 1, but it contains less of good 2. Okay? So this is kind of the mathematical framework, where we will draw bundles of goods and in some sense will represent the consumer's decision making. We call this entire space commodity space. Let's see, double M. Commodity space. Okay. Now, we've just used 2 goods to keep things nice and simple for our first pass at this theory. Obviously, as you study economics further, next year you'll be studying this with any number of goods, and you'll be looking at, for instance, n-dimensional space as your commodity space. Okay, but for now we'll keep it in 2 dimensions so we can draw lots of nice diagrams. Now, the way we model a consumer in microeconomics is through what's called a preference relation. So we're going to need some new notation. Okay, so we will write the following. We will write A, and then I'm going to use this curly symbol like this. And we will read this as the bundle A is preferred to the bundle B. Okay? Sometimes it's weakly because of this. We'll talk about that in a second. So this means A is preferred to B, where A and B are bundles of goods. Okay, now from this we can denote what we call strict preference. So if I write this, A is strictly preferred to B, then this essentially means that A is preferred to B in the weak sense, and we could write B is not preferred to A. Okay, so we just strike out that and say A is preferred to B, but B is not preferred to A, means A is strictly preferred to A. Okay, so the notation is similar to the greater than or equal to sign. Okay. The next notion is incredibly important, and that's the notion of indifference, okay, which is going to use this curly symbol here. So we write this. Now, it's very, very often you will hear the phrase A is indifferent to B, but it's much better to say the consumer is indifferent between A and B. Okay? Again, very often you'll hear people say A is indifferent to B, but bundles don't have preferences, people do. So it's better to say the consumer is indifferent between A and B. Okay? Now, technically, this essentially means that the consumer prefers, in the weak sense, A to B, and also B is weakly preferred to A. Okay, so if both of these are true, in a sense, he likes them exactly the same amount. And that's the key interpretation here. So if the consumer is indifferent between two bundles, it does not mean he doesn't know what he likes. It means he knows what he likes them exactly the same. Okay, so that's the notion of indifference. In microeconomics, we model a decision maker, or we describe their preferences using these preference relations, and we imagine that they make decisions by maximizing this preference relation in some sense, choosing the most preferred object. Remember, the basic assumption of microeconomics consumer theory is that out of all the things that a consumer can afford, the consumer will choose what they most prefer. Okay? Now, we want our model to be very general. We want this to work for as many different types of consumers as possible. So we don't want to say too much about this preference relation, okay? In a sense, everybody is allowed to have different preferences, and there's nothing wrong with that. However, we are seeking to build a normative theory, okay? We're not quite studying psychology here. We're studying rational behavior. In some sense, it's an idealized version of behavior. Okay, so when we talk about rational preferences, we're going to explain exactly what we mean by that. So rationality, in some sense, making decisions in a way in which you would want to make decisions. Okay, we're going to describe this using some very basic axioms. Okay, so preferences are going to be kept very general. We're allowed lots of variation in different people's preferences, but we are going to insist that these preferences obey certain rules, and we call these rules axioms. Okay? There are 3 of these axioms, which we'll talk through now: the axiom of completeness, the axiom of transitivity, and the axiom of monotonicity. Now, the first 2, completeness and transitivity, are really the important ones as far as defining what we mean by rational. In fact, in many texts, completeness and transitivity together are essentially the definition of rationality. So it's not a very, very strict definition of rationality. It's only requiring two things be true. Monotonicity we will use, I will explain it further. We use it for convenience and it's natural in many circumstances. So let's talk about the axiom of completeness. Essentially, this says that rational decision makers, they know what they like, okay? Now, remember, indifference does not mean I don't know what I like. It means I like two things the same, okay? In real life, it's perfectly natural to say you don't know what you like, and maybe you need more information, and so on. But for a rational decision maker, we're going to assume away this complexity and just say they know what they like. So let's read the axiom. Axiom 1, completeness, says for all bundles A and B, exactly one of the following always holds. The consumer strictly prefers A to B, or the consumer strictly prefers B to A, or the consumer is indifferent between the bundle A and the bundle B. Okay? Now notice that the axiom is saying that these are mutually exclusive. So if, for instance, the consumer strictly prefers A to B, then the axiom of completeness is also ruling out that he strictly prefers B to A or that he is indifferent. Okay, so exactly one of these is true. Okay, so it rules out the possibility of the consumer not knowing which bundle is preferable. And it also rules out the possibility of the consumer having kind of confused preferences where they strictly like one thing better than another and the reverse also being true. Okay, so that seems natural given that we're talking about a rational decision maker. The next axiom is called the axiom of transitivity. Okay, and this is going to do a lot of the heavy lifting as far as our definition of rationality is concerned. Now, one way to think about transitivity is to think of it as a consistency requirement that the consumer is able to put things in order. So they're able to take several bundles of goods and put them in order of which they like from best to worst. Okay, so let me read the formal definition. It says that for the axiom 2 transitivity says, for all bundles A, B, and C, the following implication holds. So if our consumer prefers A to B and the consumer prefers B to C, we don't need to ask him if he prefers A to C. We are simply going to assume that the consumer prefers bundle A to bundle C. Okay? So essentially this is putting his first two requirements, if he prefers A to B and he prefers B to C, have in some sense already put A, B, and C in order, and we're going to assume that that order is consistent. The consumer also likes A better than C. The same, we will also assume the same holds for strict preferences and also for indifference. So if the consumer is indifferent between A and B and indifferent between B and C, then he is indifferent between A and C. So let's have a quick look at what happens when this axiom is violated. So let's have a look at the axiom of transitivity. So one more time, transitivity says that if the consumer prefers A to B and the consumer prefers B to C, okay, so they're comparing 3 bundles of goods, then I don't need to ask them whether they prefer A to C. I am going to assume that they do. Okay, so then the axiom will require that the consumer prefers A to C. So why would we include this in our definition of rationality? Okay, so, well, let's have a look at what happens or what goes wrong when we break this rule. So a violation of transitivity could look something like this. Suppose that the consumer strictly prefers A to B and that they strictly prefer B to C. Transitivity requires that they strictly prefer A to C, but let's suppose that they violate this and the consumer prefers C to A. Now you can see what's happened here. We end up with a cycle. Okay, so imagine our consumer goes to the market one day and they have bundle A in their pocket. They meet somebody who has bundle C. Now, our consumer strictly prefers bundle C, so he exchanges A for C, perhaps spending some money. Then he spends some more money to buy bundle B in exchange for bundle C. But given that he likes A better than B, he then spends more money and he has bundle A. And now he has bundle A and he spends more money and more money and more money, going round in circles until he runs out of money. So in some sense, he becomes economically extinct. Okay, so it's kind of a Darwinian argument. This guy is not allowed into our economics classroom. Okay, so this is sometimes called a money pump. And it's the kind of thing that we want to exclude from our theory. We don't want to exclude too much. We want to allow for our model to be as general as possible, but we don't want to include people who are frankly quite stupid. Okay, so that's what happens if you violate transitivity, and why we would like to keep transitivity in our definition of rationality. The next axiom we will include in our list of axioms for consumer theory is the axiom of monotonicity. Essentially, this is going to require that what we are calling goods really are good. They're not bad things. So in some sense, the consumer will always want more of them. Okay, now sometimes this is called non-satiation. Okay, never satisfied. The consumer has never had enough. So before we state the axiom, let's just quickly jump back to paper to develop some notation. So to state the axiom of monotonicity, we're going to be comparing the size of bundles. So let me just go through some notation. When I write the bundle A is greater than or equal to the bundle B. Now remember, these are two-dimensional objects. So what I'm saying is that this two-dimensional object A1, A2 is in some sense greater than this object here, B1, B2. Okay? So what this notation means here is that A is larger in the first coordinate, okay, and A is large, A2 is larger than B2 as well, or at least as large as B2. Sorry, B1 and B2. Okay, so to say one two-dimensional object is greater than or equal to the other means that it is larger in both coordinates. For example, if I have a bundle 2, 2, that is greater than or equal to the bundle, let's say 2, 1. Okay, so the first coordinate is the same, so that's okay. And the second coordinate, 2, is larger than 1. Okay, so that's what we mean by this notation. When we write that a bundle is strictly greater than another bundle, okay, what this means is that it means that the A is at least as large as B in this sense, and it means that they are not equal. Okay? So that's covered by this case here as well. Here I could say A is strictly larger than B because it satisfies this, and they are not the same. Okay, so it rules out comparing 2, 2 with 2, 2. That would not be strictly greater, that would be equal. Okay? Another notation you'll see sometimes is that if we write A is strictly greater than B, but we use two of these strictly greater than signs, means that A1 is strictly greater than B1 and A2 is strictly greater than B2. Okay? So the greater than or equal than sign, we just need to know how to interpret it when we're using vectors of 2 dimensions or more. Okay, this readily extends to however many dimensions we're working in. So let's get back to stating the axiom of monotonicity. So let's state our axiom of monotonicity, the third axiom of consumer theory. I think the book calls this the more is better condition. So formally, the statement reads as follows. For all bundles A and B, if A is larger than B in the weak sense, then A is preferred to B in the weak sense. Okay, and we could also add the strict version if A is strictly larger than B. Okay, so it's greater than or equal to in both coordinates, but A is not equal to B, then A is strictly preferred to B. So why would we add the axiom of monotonicity? Well, several arguments. First of all, it's because we're really assuming that goods are actually good. So in some sense, we justify it by the definition of a good, something we want more of. It's never a bad. The second reason is that in real life, it's quite compelling. Typically, people want more than less. Okay, this is not always the case. Maybe after 5 pints of beer, the 5th one is a bad idea, for example. But typically, more is better. In particular, if you can sell any extra units that you receive. And finally, it's going to make our analysis simpler. Okay, so using the axiom of monotonicity will simplify much of our analysis. However, even though there's good arguments for it, and we will use it, it's not strictly part of the definition of rationality. It's an additional assumption. Rationality is completeness and transitivity, and we will use monotonicity so much that it's worth including in our set of axioms. So let's introduce an idea called indifference curves. We've already seen that we can represent bundles of goods in a diagram in 2 dimensions in our commodity space diagrams. How can we represent preferences in this diagram? Okay, so the tool we're going to use is called an indifference curve. Okay, now the formal definition is of essentially, if I take a bundle A, I'm going to write the indifference curve or the indifference set associated with that bundle will be the following. Now, this is called set builder notation. Okay, so if you haven't seen set builder notation before, it's worth just searching for it online. You'll find it very quickly. It's not too difficult. But let's just learn it in context now. So the indifference curve associated with bundle A, it's going to be a set. So I'm using a curly bracket, and it's going to be all of the different bundles B that satisfy the following condition. So the colon denotes here we have the typical members of the set, and then after the colon is the rule they must satisfy, and the rule is our consumer is indifferent between A and B. Okay, so this is a set. It contains lots of different bundles, possibly, and each of these bundles satisfies this rule. Our consumer is indifferent between A and B. Okay, now when we represent these in commodity space, let's have a look at they can take all sorts of different shapes, really, depending on the consumer's preferences, of course, each person being possibly unique in some way. But let's draw a diagram of a typical set of indifference curves. So remember, let's label our diagram. There's 0. This axis denotes the amount of good 1 in any particular bundle. The vertical axis denotes the amount of good 2 in any particular bundle. And let's suppose that our consumer is indifferent between 2 bundles, A and B. Okay, and A is here and B is here. okay? Now, an indifference, so to say that our consumer is indifferent between these two bundles, we can now use our language. A and B are on the same indifference curve. Okay, so indifference curve is kind of a fictional concept. It's an idea we've cooked up, but we're saying something that can be observed in the data. Our consumer likes these two things. We'll translate that into these two objects are on the same indifference curves. And there may be lots of these on any particular indifference curve. And we often draw, well, this is the kind of typical shape you will see in lots of economics books, a nice curve like this, okay? So that's very typical. What about if C is strictly preferred to A? Okay, well, then C is not on this indifference curve. Now, we wouldn't expect it to be down here, really, when we think about our axioms. We'll talk more about that in a minute. But if I look at a bundle down here, it's got, if I compare it to A, it seems to have less of good 1. So there's A1. And here is this amount. And it has less of good 2 as well. Okay, so C is probably somewhere above this indifference curve, perhaps here, but it lies on another indifference curve that perhaps looks something like this, okay? And if I write C, the consumer is indifferent between C and D, then I know that D lies somewhere along this curve like this, okay? So this is called a preference map, okay? And it's something we're constructing as a way of representing the actual data about a consumer's tastes between different objects of bundles. Okay, so we could well imagine offering a consumer lots of different bundles of goods, asking them which they like. They prefer some bundles to others. They're indifferent between some bundles. And we can organize that data into a preference map in commodity space. Okay, so that's an indifference curve. Now, we're going to discuss the properties of these indifference curves. We've already written down 3 axioms. So these indifference curves will inherit certain properties from those axioms. So let's go through them next. So now that we've written down the axioms of rational choice, the axioms of completeness, transitivity, and our additional axiom of monotonicity, we can, this notion of an indifference curve is a concept that we've derived, okay? So it's a tool we've come up with to use as a way of organizing and representing the consumer's preferences in a two-dimensional diagram, or more dimensions if there were more goods. Now, given that we assume the axioms of completeness, transitivity, and monotonicity are indeed true, and that's all we assume, what can we say about these indifference curve? Well, the following facts can be established. So first of all, bundles further from the origin are better. Now, hopefully that's quite clear from the definition of monotonicity. If I, for instance, consider the 45-degree axis in our diagram, where all bundles have the same number of each good, then clearly going higher and higher and increasing the number of goods in the bundles, of all goods, is just making the bundles better and better and better. That's what the axiom of monotonicity says. So we can kind of translate our initial idea of the consumer wanting to choose the most preferred object into our own made-up language. The consumer wants to choose a bundle on the highest indifference curve possible, on the indifference curve that is furthest from the origin. Okay? Second, it's a consequence of our assumptions, the axiom of completeness, that every bundle lies on an indifference curve. Okay, so there's no bundle which is not on an indifference curve. That is to say, if we draw a commodity space diagram and pick any point, there is an indifference curve that goes through it. Okay? That's sometimes called the denseness property of indifference curves. Now, the next 3 properties are take a little bit more work to prove, so we'll go through each of them in turn. I'll just mention them now. First of all, indifference curves cannot be thick, thick in inverted commas. So if we remember the kind of ancient Greek definition from geometry of what a line is something that has zero width. Okay, so indifference curves cannot have any width at all. That's one thing we can prove. They must be perfectly thin in a mathematical sense. Next, we will prove that indifference curves must slope downward. Now, I drew them that way to start with, but there was no particular reason yet. We hadn't proved they had to look like that. So we will prove that indifference curves, they have no portion anywhere which slopes upwards. And the final thing we'll prove today is that these indifference curves, they cannot cross, okay? They cannot intersect each other. And that takes a little more work to prove. So let's go through these final three statements in turn now and prove each. So let's prove our first claim about indifference curves, that indifference curves are perfectly thin. They have zero width. Now, I've already drawn a commodity space diagram here and labeled the 0, and that the horizontal axis is good 1 and the vertical axis is good 2. So I'm ready to start drawing indifference curves in this commodity space. Now, to prove that indifference curves are perfectly thin, they have zero width, we're going to use something called proof by contradiction. Now, don't worry, this may sound like something you haven't heard before, but trust me, you have heard it before. The idea is we assume something is true, and then we develop a contradiction, and then by doing so, we know that our initial assumption was false. So, for instance, if I wanted to prove to you that numbers are infinite, I might say, well, let's suppose there was a biggest number. Okay, that's our assumption. There is a biggest number. And then if I add 1 to that number, I get a bigger number, which contradicts my assumption that there is a biggest number. Okay, so you've seen proof by contradiction before, even if it wasn't described as such. So how does it apply here? Well, for the sake of contradiction, suppose an indifference curve really was thick, so it had some width. So for instance, let's suppose an indifference curve, that's the typical shape we draw, but let's imagine it's quite thick. I'm drawing it very, very thick, and I'm imagining that this entire space kind of between these lines, if I very roughly shade it, that this entire shaded in area represents one indifference curve. Suppose that was true. Well, what's happened? So let's write our kind of suppose an indifference curve was indeed thick. Okay. Now, by the definition of an indifference curve, if I pick two bundles, now I'm going to write bundle A here and bundle B there. Okay. So by the definition, because this is an indifference curve, I know our consumer is indifferent between A and B. Okay, so there I've just appealed to the definition of an indifference curve. This thick one I've drawn must satisfy that definition if it's an indifference curve. Okay, now clearly if I look at the diagram, all right, clearly, here if I've drawn bundle B so that it's bigger in both coordinates. So B1 is strictly greater than A1, okay, has more of good 1, and B2 is greater than A2, okay? So what can I say this? So by, I'll just write axiom 3 to save space, but by the axiom of monotonicity, we know it's strictly greater that our consumer, our consumer must strictly prefer bundle B to bundle A, okay? So now we've arrived at the the point where we have two different preferences being expressed. By definition, our consumer is indifferent between A and B by the definition of an indifference curve. But because the indifference curve was thick, we are able to draw an example such as A and B, where B is greater than A, which by monotonicity, the consumer must strictly prefer B to A. So what's gone wrong here? Well, if we remember by the axiom of completeness, the completeness axiom said that exactly one of the following is true for all bundles. Our consumer strictly prefers A to B, he strictly prefers B to A, or he is indifferent. So the fact that we have two distinct preferences, this final sentence, and this final sentence is the one that gets forgotten the most. Most people get to hear and then say contradiction, but what is it contradicting? This contradicts the completeness axiom, because the completeness axiom said exactly one of each kind of preference, of each of the kind of preferences can be expressed. Okay? And this is the only time, at the end of a contradiction, it's the only time you're ever allowed to write an exclamation mark in economics or mathematics. When you develop a contradiction, you're allowed to do that. Okay? So hopefully you can see the logic here. To argue that indifference curves must be thin, we said, well, suppose an indifference curve was indeed thick, and also that the axioms for our consumer theory model were still true, so completeness, transitivity, and monotonicity, then what happens? Well, using them kind of four ideas that three axioms hold, and there is a thick indifference curve, we can develop a contradiction that completeness gets violated. Okay, so that's why indifference curves must be thin. So let's now prove that indifference curves, as well as being thin, they must slope downwards. Okay, so indifference curves must slope downwards everywhere. They have no portion that is upward sloping. Okay, so to prove this, it's very, very similar to the proof that indifference curves are thin. We'll do a proof by contradiction and say, suppose, I won't write it all out, but if you consult the slides, it's there. Suppose that an indifference curve had some portion that was actually upward sloping. So if it looked something like this, it was maybe downward sloping for a bit, but then increased and then went down. Okay, so if this is an indifference curve, and I can see here it has an upward sloping part. Okay, so what's wrong with this? Well, here I can just label two bundles A and B, and if I choose them in the right place, the argument will work. So again, what can I say about A and B? Well, by the definition of an indifference curve, our consumer is indifferent between A and B. Okay, they are on the same indifference curve, if and only if the consumer is indifferent between these two bundles. Okay, so that just appeals to the definition of an indifference curve. Again, I can make the same argument by the way I've drawn it, clearly that the bundle B has more of good 1 than bundle A, and it has more of good 2 as well. It's larger in both coordinates. Okay, so by the axiom of monotonicity, axiom 3, what do I know? Well, larger bundles must be preferred. So our individual must strictly prefer bundle B to bundle A. Okay, so I've developed two different preferences here. Okay, is there a contradiction? Yes, there is. But what precisely is being contradicted here? Well, it's the axiom of completeness. Completeness said for any two bundles, exactly one type of preference must hold. The consumer either prefers A to B, or they strictly prefer B to A, or they are indifferent. So here we have contradicted by finding that the consumer is both indifferent between A and B and also strictly prefers B to A, this contradicts completeness. Exclamation mark, because it's a contradiction. Okay, so that's why indifference curves must slope downwards, and they must slope downwards everywhere. Now, they can be kind of strange shapes. Okay, this doesn't rule out something that kind of comes down and keeps coming down at strange. As long as none of these single portions slope upwards anywhere, this is perfectly allowed. Okay, so that's another indifference curve, and it's permitted by the axioms of rationality. It looks unusual, but people are unusual, okay? But this is not allowed. This upward portion here is something that we will simply rule out using the definition of an indifference curve, using the axiom of monotonicity, and using the axiom of completeness. Okay. So let's prove our final property of indifference curves, and this is the fact that indifference curves, ICs, cannot intersect. Okay? The idea of indifference curves intersecting is not compatible with the axioms of consumer choice, is what we're going to show. Well, we'll do another proof by contradiction. Now, trust me that proof by contradiction is used an awful lot, but it's certainly not the only method of proof you'll see on this course, and certainly not in other courses. Okay, but we've used it three times in a row here. So I thought I should just mention that there are other types of proof. But here we were going to write, suppose that two indifference curves intersected. Okay. A nicer way to write this would be to say, suppose, comma, for the sake of developing a contradiction, comma, that two indifference curves did indeed intersect. So let's draw this, and so I'm going to draw them downward sloping because I know that they are downward sloping, and I'm representing them. Obviously, I can't draw them perfectly thin with this Sharpie pen, but they are perfectly thin. They're representing something that's perfectly thin. So let's label a few points. So this is a case of two indifference curves, indifference curve 1 and indifference curve 2, and they intersect at this point. Let's call this point here, let's call C, okay? And let's put a bundle down here, A, and let's put a bundle over here called B, okay? So this is the situation represented by when two indifference curves intersect. So what can we say about this? Well, appealing to the definition of an indifference curve, so by definition, the fact that these bundles are on the same indifference curves, for instance, A and C are on the same curve, we know that our consumer is indifferent between A and C, and we know that our consumer is indifferent between C and B. Okay? This is just applying the definition of an indifference curve, translating this diagram into kind of symbol representation. So this is what we've drawn. Our consumer's indifference between A and C, and his indifference between B and C. Okay? Now, if I know two preferences that involve, and I'm just looking at three bundles, I don't need to ask another question, okay? So I know that by the axiom of transitivity, that's right, transitivity implies, or perhaps even transitivity requires, if our consumer is indifferent between A and C, and between C and B, then I don't need to ask him about A and B. Transitivity requires that this consumer is indifferent between A and B. Okay. So that's nice. What can we do next? Well, the way I've drawn B, it's clear from the diagram that B is larger in both coordinates. So it's a larger in two-dimensional, comparing to two two-dimensional objects. So this is a vector inequality. B is larger than A. Okay, it's at least as large in both coordinates, and it's not the same bundle. It's strictly larger. Okay, and so what do we know? Monotonicity, our third axiom, requires that our consumer strictly prefers A to B. Okay? So now we're in business. We've got two different preferences being expressed for the same two bundles. The consumer must be indifferent between A and B. We've shown that must occur when these indifference curves intersect, and also that there exists a B in this appropriate position such that the consumer must also be strictly prefer B to A. And don't forget this final sentence, this contradicts. And what does it contradict? Contradicts the axiom of completeness. Okay, so the assumption that two indifference curves intersected, when we assume that three axioms of consumer theory hold, led to the contradiction that one of the axioms didn't hold. It was being violated. Okay, so essentially our initial supposition was incorrect, and it must be the case that indifference curves never intersect. In the next lecture, we'll continue our work on consumer theory and develop more tools so that we can, first of all, rephrase the consumer's problem. The consumer's problem is just to choose the thing they prefer the most that they can afford. We've already seen that choosing the most preferred could be translated into find the bundle on the highest indifference curve. The first sentence, choose the thing you most prefer, is in plain English that everyone would understand. The second sentence, choose a bundle on the highest indifference curve, is language that we're inventing, and it turns out to be very useful because this is how we're going to model the consumer making choices, by translating it into a mathematical model, defining concepts that are equivalent to making the choice of the most preferred, subject to being able to afford that choice. And then when we translate it into a mathematical model, we'll be able to analyze the properties of these choices and how they change as prices change and so on. So lots of interesting things ahead of us. I'll see you next time. In the meantime, take care.